Hello, good night, good evening. Tonight I'm going to be explaining a little bit about the heart and how it works. First, I want to start off with the different cardiac action potentials. There's two different types of action potentials in the cardiac muscle cells. We'll start out with the actual, um, sorry, the cardiac, the majority of the muscle cells in the heart, besides the pacemaker cells. So they're going to have an interesting looking action potential graph if we draw it here. So let's say this is around -80, threshold about here, and then up here is about +20. So the resting membrane potential of these cells is going to be a lot lower than we've seen with any other muscle cells. Here we go. The reason for the low resting membrane potential is because of high membrane permeability to potassium. So I'm just going to write out. There's four different phases here: phase 4, phase 0, phase 1, 2, 3, and then back down to 4. So the fourth phase is RMP. Like I just said, it's going to be a lot more negative than normal just because of high membrane permeability to potassium. There's going to be these potassium channels that are open during RMP, and they have a current called IK1. And this channel is going to allow for calcium to constantly be staying outside of the cell because it's positively charged. That's going to leave negative charges in the cell, and so that charge on the inside the cell is going to be pretty close to the potassium um, Nernst potential. So we're just chilling here at RMP. Then at phase 0 is going to be depolarization. So what's going to happen here is at phase 0, there's going to be voltage gated sodium channels. They're going to sense an action potential and they're going to open. So the voltage gated sodium channels open. As this happens, as we can see right here, that's going to cause a sharp uprising in the charge. And as this happens, when threshold is hit, the potassium channels are going to close. So that's going to cause a sharp increase in the membrane potential in the charge of the cell until we reach a certain point here around +20, and that's when rapid repolarization is going to start. So we're going to have an initial rapid repolarization. And at this rapid repolarization, our sodium channels are going to close, and a couple of potassium channels, not the same ones as before, um, are going to open, and then also some chloride channels are going to open. And we call these the current of TO1 and TO2. And so this is potassium leaving the cell, chloride coming into the cell. And so that's just going to make the cell a lot more negative in a quick amount of time. But as you can see, there's this plateau phase here, and what causes that is a delayed influx of calcium. So plateau phase, what's going to happen is there's influx of calcium. So the calcium channels are going to open up. They're delayed from the sodium channels, and that's why there's this delayed plateau phase. The reason for the plateau phase is it's actually going to help our muscles prevent tetany. So there's going to be a complete rest in between each contraction of the muscle. Um, and obviously, we don't want tetany in the heart because if our heart is not pumping blood, or if our heart is only contracting and not relaxing, there's no space for blood to come back into the heart. Relaxation is very important. So that's we have our plateau phase. And here, when the calcium enters, that's actually when contraction is going to begin. The calcium is going to bind to those troponin, to the troponin, and the myosin will be able to bind to the actin and cause contractions. And then calcium will be calcium coming in, but eventually more potassium channels actually open up, and they're actually gonna outweigh the calcium channels. We're gonna have this third phase right here, which is called repolarization. I'll write that up. I'll write that up here. Repolarization. And here, so more potassium channels open, and as we cross um, over threshold, the calcium channels are going to close. RMP is going to be reestablished, and then our original current is going to, um, or these potassium channels here are going to open up again, and so we're going to be back at phase 4. So that's our cardiac muscle cell action potential. As far as our other one, the autorhythmic cells, they're going to be a little different, but I just first want to talk about something called ATP sensitive potassium channels. So during times of hypoxia in the heart, which is when there's not enough oxygen to the cells in the heart, there's a potassium sodium ATP pump that's maintaining this gradient that's helping our cells stay at such a negative threshold. So that's obviously going to stop working, and the concentrations of sodium and potassium are both going to be affected. So that can cause something called arrhythmias, which are spontaneous depolarizations. The ATP sensitive potassium channels are going to sense low ATP, and what they'll do is open up to help keep the cell RMP below threshold. So they'll let more potassium back into the cell, or back out of the cell, sorry, and try to maintain that low RMP just to prevent those spontaneous depolarizations. So it's good to go over that. Let's go move on to the autorhythmic cells. Graph is going to look a little different. Threshold here, down here is about -60. And then up here, +20. And we're going to have just 3 phases in this one. So we're going to have phase 4, phase 0, and phase 3. Phase 4 is going to be a gradual depolarization. What's going to happen here is something called HCN, or funny channels, will gradually open. So basically, once the the charge of the cell goes below threshold, these HCN channels are going to open, and they're going to gradually let sodium into the cell. So they're slowing down the repolarization, it stops, and then they're slowly depolarizing the cell until they reach threshold. Once threshold is reached, which is phase 0, depolarization will begin. I guess a more rapid of depolarization. And what's going to happen is L type, which means kind of like long-lasting, calcium channels open. So these L-type calcium channels are going to open, and that's going to cause a more rapid depolarization. It's going to come up like this. That's also going to cause contraction of those cells. The reason that this peak here is more rounded out than before is because the calcium channels take longer to close. So they're starting to close, closing more, and because of that, it's going to take, it's going to have that rounded effect. And then our last phase here is going to be repolarization, obviously. Here, potassium channels are going to open, causing repolarization until we hit threshold again, and we enter stage 4. So potassium channels open. And we'll go back down to threshold. So that is our autorhythmic cell, and the purpose of these autorhythmic cells is to maintain a heartbeat. So these cells are going to be signaling to the rest of the cardiac cells when to contract. And that actually segues perfectly into our next topic, the EKG, the electrocardiogram. So if I just draw a little cartoon heart here, we have our 4 chambers, the atriums and ventricles. And then we have a couple different landmarks here. We've got the SA node. And then here in the middle is our AV node. And what's going to happen with the electrocardiogram is it's going to be picking up electrical fields or electrical impulses from the heart. So different differences in the electricity of the heart are going to cause things to change. So if we just draw this out here, say we have 4 cardiac cells lined up. At resting membrane potential, all of these cells are going to be negative on the inside and therefore positive on the outside. So let's say we have our sensors here, positive and negative. What's going to happen is a signal is going to come and a wave of depolarization is going to come across these cells. So if we just copy paste this, so wave of depolarization is going to happen. So let's say these first 2 cells depolarize. They become positive on the inside and negative on the outside. Well, what's going to happen is this negative wave on the outside is going towards our positive electrode here. So we've got a wave of negative coming towards a positive, and what that is going to cause is it's going to cause a bump in our cardiac reading. And once this wave is completed, obviously it would be finished off and kind of look like that. So every time there is any kind of electrical wave or signal going around in the heart, it's going to be picked up by this electrocardiogram. And I'll just erase this so it's accurate again. So usually with a normal heartbeat, we're going to see a couple of different waves here, and luckily they're all in alphabetical order. P, Q, R, S, T. So I'm just going to go through all of these different waves. So our first waves are going to start up way up at the SA node as the atriums depolarize, causing contraction. So it's going to start something like this and kind of move outward to the entire atria. And when that happens, obviously, like we drew below, we're going to have negative charges going in to this positive outside of the heart. And when we have a negative tail going towards a positive electrode, that's going to cause our bump. So our P wave is going to be the depolarization of the atria. Then once we get to our AV node, there's going to be a delay, and that delay is just so that the atria and ventricles are not contracting at the same time. But once that happens, our AV node is going to start the depolarization of the ventricles. And the very first place that it's going to start from is this part of the left side of left ventricle, the interventricular septum, and it's going to send an average vector out this way. So we have our negative charges coming out from here, going out towards the positive ventricle. And so that average vector is going more towards the negative electrode than the positive. Negative to a negative is going to cause a dip in our electrocardiogram. So our Q wave is actually showing the depolarization of the interventricular septum. I guess the initial depolarization of the interventricular septum. But quickly, the entire ventricles are like all of the ventricle is going to be depolarized, and so it's all going to come down this way, and we'll have a large average vector with a negative tail going towards our positive electrode. That's what's going to cause our R wave. So that's the depolarization of all of the ventricles. And then the last part of the ventricles to be depolarized is this spot up here on the exterior left ventricular wall. And that is going to cause an average vector to go more towards our negative electrode. And so we have negative going towards a negative. That's going to cause a dip. So that's what our S wave is going to be. That's that last part of the thick left ventricular wall. And then our T wave here, obviously at this point we have a little phase right here between S and T where there's no increase or decrease. That is where the entire heart is actually negatively charged on the outside. So it's time for repolarization to occur. Repolarization is going to happen in this direction. Oh, let me draw. Repolarization is going to happen in this direction. And now instead of having a negative tail, we're going to have a positive tail. So we're going from epicardium to endocardium is going to be our repolarization. And that is going to cause our big T wave as the entire heart repolarizes. So that's the basics of our EKG. Now let's talk about a couple things that can go wrong with EKGs. There's something called current of injury. And so that's basically when something is wrong with the heart and it's causing the EKG to read a different baseline than what is actually should be the baseline. But first, let's talk about some inverted T waves. I cannot write T waves. So our normal EKG graph is going to look like this. But if we go to our inverted T wave, I can just draw that real quick. It's going to look something totally normal, but then at the T, it's going to be inverted. And the reason for that is something called hypoxia. So hypoxia is when there's not enough oxygen supplied to a cell. And in this case, we're starting to get some slight hypoxia in some of these ventricular cells. So if that hypoxia kind of starts in the endometrium, just because that's further away from the coronary arteries, those are going to be the first cells to not get oxygen. So what's going to happen is there's going to be the activation of those ATP sensitive potassium channels that we talked about earlier, and they're going to cause a quicker repolarization of the endocardium than the epicardium. So up here we were saying from that the T wave is from epi to endocardium. Down here, because of hypoxia, it's going to be from endocardium to epicardium. And what that's going to cause is a positively charged tail going towards a positive electrode, which will cause our inverted T wave. So that's some slight hypoxia. Now, what happens if the hypoxia gets worse and our cells start not being able to repolarize? Well, that's where something called NSTEMI and STEMI come in. So let's just draw the EKG for an NSTEMI and see how it is compared to a normal EKG wave. So, sorry. Everything looks normal, but all of a sudden here at our S wave, whoa, we're going way further down, and then we come back up to this original baseline. So as you can see, NSTEMI stands for not AST elevation. So here, this is basically an ST depression. And what's happening is, if we draw another heart, we've got our negative up here, positive down here. If we get enough hypoxia in these endometrium cells, they're unable to repolarize. So at resting membrane potential, if the whole heart is relaxing and the whole heart is showing these positive, is have all the heart cells have positive on the outside, our endometrium cells here are going to have negative charges on the outside because they're not able to repolarize. And what that's going to cause is going to cause a constant vector going towards the positive electrode, which is going to cause a bump, right? But if it's constant, instead of being a bump, it's just going to be a straight line above where the baseline should be. So here in our NSTEMI graph, we can see the original baseline where it should be, but because of this constant signal being sent to the EKG, there's a heightened baseline. So that's what's happening with an NSTEMI. And once that hypoxia gets even worse and it affects the entire wall, that's when something called a STEMI happens, which is a elevated ST interval. So if I just copy this heart, So what's going to happen is instead of just part of the wall, it's going to be the entire wall. Now this, instead of sending an arrow towards the positive electrode, it's going to send an arrow more towards the negative electrode. So kind of up, but more towards the negative electrode. That's going to cause a dip in our normal baseline. So let me just draw this. So this is what our baseline we think it is. It's going normal, P, Q, R goes up, and then it should come back down to that baseline, but instead it goes to this baseline, goes up to the T wave, and then back down to that baseline. So this right here is what our baseline should be at the S, and the reason that it shows this original baseline in the reading is because when all of the other cells besides the hypoxic cells are depolarized, the entire cell is going to be reading negative, so there's going to be nothing for the EKG to read, and it'll show the original baseline. But at these points here, in between, the baseline is going to be lower just because of that constant reading on the EKG from the hypoxic cells in the wall of the ventricle. Next up, we'll briefly cover norepinephrine and acetylcholine. CH. And basically, norepinephrine and acetylcholine are both going to be tools of the sympathetic and parasympathetic nervous systems to affect things like heart rate and the intensity of heart contractions, how fast the heart loosens. And these things are called inotropy, which equals intensity. That's how I remember it. And then chronotropy, I remember it as clock or heart rate. So norepinephrine is an adrenergic stimulant. So it's going to come around, and our heart cells have beta 1 receptors. So our norepinephrine comes, it's going to activate the beta 1 receptors, and these beta 1 receptors are going to increase our inotropy or intensity, and they're going to increase our chronotropy or heart rate. But if we have acetylcholine, which is that binds to muscarinic receptors, it's going to bind to the M2 muscarinic receptors. This is going to decrease heart rate and decrease inotropy. So just a couple ways that the blood is able to regulate the heart rate just using those norepinephrine and acetylcholine. Now let's kind of go, we've talked a lot about the cardiac muscle contraction. Let's actually map out what is happening and where. So we'll start with how contraction happens. So let's just draw out a big blown up heart cell. So we're going to have an initial Buang coming in to this T-tubule. The Buang is going to trigger V-gated calcium channels to open. So when those open, calcium from the ECF is going to rush into the ICF of this heart cell. Now, this is where it gets a little bit different than muscle cells. the calcium is actually required to release more calcium from the sarcoplasmic reticulum. So here we have our sarc, and in our sarc we have some ryanodine receptors or ryanodine channels with a receptor for calcium. So calcium is going to come and bind to the ryanodine, and it's going to release more calcium from the sarc out into the ICF. Now this calcium is going to go ahead and bind to troponin, just like with skeletal muscle and smooth muscle. That's going to remove the troponin from the actin, and the myosin is going to be able to bind to the actin and cause contraction. Now, the next part, relaxation. Eventually, the calcium is going to unbind from the troponin. Um, the myosin heads are going to unbind from from the actin, and it's going to cause relaxation. Here we have another sarc. Calcium's going to come off. Some of the calcium is going to be pumped back into the sarc using ATP calcium pumps. And then here we have our closed RYR, ryanodine channel. And then some of the calcium is actually going to be pumped back into the ECF. And it's going to be sent back out to the ECF. As it is pumped out, three sodiums will come in. And then to maintain this gradient so that the sodium can help the calcium come in, there's going to be another ATP or sodium potassium pump, as we've seen before. So that same sodium only has one positive charge on it, and then potassium comes in. That's going to maintain our gradient. So that's how the different ions are going to travel in and out and cause contraction in the cardiac cells. And lastly, let's quickly go through the cardiac cycle. So there's a really good graph that kind of shows and demonstrates what's happening in the ventricles. So basically, pressure is one of the best ways that we can illustrate this. We're going to have the pressure of our ventricle, our atrium, and of our aorta. So the atrium pressure is going to kind of start out like this, and our ventricle pressure is going to be lower than the atrium. So the atrium is going to be letting blood is going to be kind of passively putting blood into the ventricle and topping it off. Eventually, though, the ventricle's pressure is going to get higher than the atrium. That is going to cause the bicuspid valve to close and an increase in pressure in the ventricle. This is where the heart is contracting, and up here we have the pressure of the aorta. Once the pressure of the ventricle gets higher than the pressure of the aorta, that's going to cause the opening of the semilunar valve. So this is going to go up, come back down. Pressure of the aorta is going to follow closely to the pressure of the ventricle. It's actually going to go above it and come down. And then we're going to have a little dip right here. It's going to go back to normal. And the ventricular pressure will eventually return to below the atrium pressure. And that's when our bicuspid valve will open back up. So, right here, opening bicuspid here, or no, sorry, this is closing of bicuspid. Right here is going to be opening of the semilunar. And then right about here is where the semilunar will close. Semilunar. And then right here is where bicuspid will open again. Okay. As far as volume goes, the volume of the ventricle is going to be increasing during this period. When all the valves are closed in between these 2 points right here, there's going to be no pressure change, or volume change, sorry. Then, once the semilunar valve opens, there's going to be a decrease in volume. Again, there will be no valves open, and then increase again. So right here, increase, this is called isovolumic contraction. And this is isovolumic relaxation. Okay. I already talked about the opening and closing of the valves. Now let's just talk about the lub-dub noises. So when the bicuspid closes, it's going to cause our lub. And when the semilunar closes, it's going to cause our dub. Lub, dub. If there is a sh after either one of these, that means that there's a hole in the lub or the dub, or sorry, in the semilunar valve or in the bicuspid valve. But if there's a sh right before the dub, that means that there is something blocking part of the aorta that's making it harder for blood to get out. And that, ladies and gentlemen, is a little bit about the heart. I hope you enjoyed. Have a great night. Peace.